Hey guys, so today I'm going to be making video 3 of the mechanics series, and I will touch on forces. And I apologize for the long gap since video 2, but I'll try to upload with more frequency from now onwards. So with that being said, I'm going to do a brief overview of the most common forces and obviously the obligatory Newton's laws. And I'll touch on forces more in later videos, including fictitious forces. So with that being said, first let's start off with Newton's laws, and there are three of them. Honestly, I feel some of them are kind of redundant because they're all basically just restatements of each other. So the first law is that a body moves with constant velocity, which may be zero unless acted upon by a force. So the velocity is constant unless acted on by force. And keep in mind that this is velocity, not speed. So if I have an object going this way at this velocity, a force would have to move it this way, even if it was still going at the same speed, because speed and velocity are not the same thing. In fact, speed is the magnitude of velocity, and I believe I mentioned that in my first mechanics series video. Okay, and his second law states that well, there's a more general version and there's the more basic one. But the basic one is just that force is equal to mass times acceleration. And as I said earlier, the first one's kind of redundant because the second one is just the quantitative version of the first one. So basically, to make an object accelerate, or in other words, speed up or slow down or experience some change in velocity, there must be a net force acting on it. Actually, let me add it in. So the sum of forces is mass times acceleration. And what I mean by net force is if I have an object or a mass and it has a force acting on it this way, and the force has magnitude F, but also has a force acting this way, which also has magnitude F, it's not going to accelerate because the net force is still zero because these two cancel out. And keep in mind, this formula only works if the mass is constant, uh, which is sort of, yeah, you can sort of see that just from looking at it. And if the mass is not constant, the formula for the sum of forces acting on an object is the instantaneous change in momentum, or derivative, the time derivative of momentum. And yeah, so this is more universal. It works if the mass of an object is changing. So for instance, if I have a car moving, then I could probably use the first one because even though the mass technically changes, the change in mass is negligible. Whereas if I had a rocket where it exhausts large amounts of mass in short amounts of time, and I wanted to calculate something like the thrust, then I would have to use the latter formula. So, yeah, that's the second one. Now, I know I didn't talk about momentum, but I will talk about momentum in a later video, so just keep this one in mind. And Newton's third law is that basically every action has an equal and opposite reaction, or every force has like an equal and opposite force. So basically, let's say you are standing on the ground, and okay, I'm not even gonna draw a whole person because I suck at drawing. Okay, so let's say this is you. So the forces acting on you are obviously, well, there's a gravitational force of the Earth pulling on you, and believe it or not, you're actually exerting a gravitational force of the same magnitude on the Earth by Newton's third law, because equal and opposite forces. So keep in mind this is the force of Earth on you, and since this one has to be opposite, this is the force that you are exerting on the Earth. And yeah, and keep in mind that they're being exerted by opposite objects. So a huge misconception is that So let's say you're staying on the ground again, and you're being attracted by gravitational force. A huge misconception is that the opposite force would be the normal force of the ground pushing on you, so that you don't accelerate down. But both of those forces are exerted by the Earth on you, so this is not a Newton's third law pair, whereas this is. In fact, we can take this one step further. So, as I said, there's a normal force that the ground exerts on you, and I'll just say this is, or not, ground on you, and you actually exert a normal force back on the ground. So, yeah, and a fun fact is actually that your weight, so if I have skill, your weight is actually a measure of the normal force that you exert on the ground, not your actual weight. I mean, if it's a flat surface, it's your actual weight, but on a ramp, it would actually be inaccurate because the normal force that you're exerting on the ground would be mg cosine theta, where theta is the angle of incline of a ramp, not mg. So this it wouldn't accurately measure your weight. So yeah, that is Newton's third law. Basically, if you exert a force on something, it will exert a force of the same magnitude in the opposite direction back on you. With that said, so yeah, these are Newton's three laws, and now I will be talking about the most prevalent forces that show up. Okay, so first of all, there's gravity, which I already talked about, and so there's basically two formulas. So the first one, as you saw up there, is just that the gravitational force is equal to mg, and this actually goes with Newton's second law, since it's g, or lowercase g, is just the acceleration. And as I said here, force is mass times acceleration, assuming that the mass does not change. And for this, we'll assume that is indeed the case. Sorry about that. But this formula only works if g is like more or less constant. In other words, if you're like close to the Earth's surface and you're much smaller than the Earth. But if we wanted to look at gravitational force between two objects of similar masses, and the distance between them could vary, then we would use a more universal formula, which I won't talk into detail in this chapter, but I'll actually, or not chapter, sorry, this video. But in a later video, I will talk about this more. But this is the more universal gravitational force formula. And yeah, I'll dedicate a whole video on this. But for now, I'm just gonna go like very surface level. Okay, next force is tension. And tension, some people write it as F sub T. I just write it as T. But tension is just the force when an object resists being stretched. So, and we see tension a lot in like pulley problems. So, for instance, if I had mass 1, mass 2, then obviously the masses would be pulling down. And then there'd be tensions exerted up. Because the string needs to resist being stretched. And this is assuming that the string is not like elastic, like a spring. In fact, I'm going to get the spring force soon. Okay, the next force is normal force, and actually up here I talked about it. So what exactly is normal force? Well, some people write it as F7, kind of like tension, and I prefer to write it as N, but normal force is any force that resists compression, and it's always perpendicular to the surface. So if you're standing on the ground, the normal force is perpendicular to the ground, and it's basically keeping the ground from crushing beneath you. So the ground is exerting this. And it's kind of, in a way, it's sort of the opposite of tension because tension resists like being stretched, whereas normal force resists compression. And as I said earlier, it's perpendicular to the surface. So if you're on a ramp now, the normal force that the ramp exerts on you goes this way, and so it's perpendicular to the surface of the ramp. And yeah, so any force that resists compression is normal force. Okay. Next, we have friction, which is a force that resists motion, and there's actually two types of friction. So I'll just I actually drew it nicely this time. Normally I suck at this. Anyways, the first type of friction is kinetic friction, and that's just how you write friction. I just prefer lowercase f. The formula for kinetic friction is mu sub k times n, where n is just the normal force. And what is mu sub k, you ask? Well, mu sub k is known as the coefficient of, and as you can probably guess, since this is kinetic friction, mu sub k is the coefficient of kinetic friction, and it resists motion when an object is moving. And so if you're usually when you're given a problem and you have to find a friction, they give you mu sub k. So for instance, a rough surface would have a higher mu sub k, whereas something like ice would have a low mu sub k. And if a surface is like completely perfect, then it would obviously have a mu sub k of 0, because then we couldn't have any friction. And yeah, normal force is just normal force. And next up is static friction, and this one isn't terribly convoluted, but it's a bit trickier. And so, as you can probably guess, since mu sub k is the coefficient of kinetic friction, mu sub s is the coefficient of static friction. And so, as you can see, this equation is sort of an inequality. So and I'll explain why. And actually, if you're at a table or somewhere right now, then I'd recommend you trying this. So, get some object on the table and try giving it a really tiny push, and you'll notice that it won't move. And since it's not moving, assuming it starts off at rest, that means that there is no acceleration, which means then that the net force is 0. So a static friction is exerted by the ground back on the object to resist this tiny push you gave it. If you give us still a tiny push, but it's slightly larger, and it hasn't met the threshold, which is this, then once again the object is not going to move, because the ground will, or the surface, whatever it is, will exert the friction back on the object. So the point I'm trying to get across here is that until you meet a certain threshold, the static friction can vary depending on how much force is exerted to move an object. Now, once you exert a big force and meet that threshold, there's still static friction exerted back, but this static friction cannot exceed the threshold. So, just as an example, so let's say I exert 50 newtons on some object, and because of the mu s and the weight of the object, let's say that the threshold is like, I don't know, 700 newtons. Well, when I exert 50 newtons, the static friction will be 50. If I exert 200, the static friction back will be 200. But if I exert 2,000 newtons of force on the object, since 700 is the max, the static friction cannot exceed 700, so it'll just be 700, which would cause the object to accelerate. So yeah, that's kinetic friction. And static friction, as you can probably deduce from the name, is a force that keeps an object from moving. Whereas kinetic friction, it starts once an object is already moving. And keep in mind, mu sub s and mu sub k are not the same. And also an interesting concept that I'll talk about more later when I lecture on like rotational kinematics and rotational dynamics is rolling. And actually how cars work is, so let's say the wheel's velocity is this way. Well, the angular velocity would actually be this way. In fact, okay, actually let me rephrase this. The center of mass of the wheel, or the wheel as a whole, would be moving this way. But the like rotation of the wheel at this point here, this bottom point, would actually be making it go this way. And if it's pure rolling motion, which I'll talk about later, the instantaneous velocity of this point here is actually zero. And what's pushing the wheel forward is actually static friction. And you might be thinking, wait a second, how come the motion of the wheel is going clockwise? Or sorry. How come the motion of the car is going to the right? And since friction should oppose motion, shouldn't the static friction also go to the right? And as I said earlier, the answer to that is that the wheel here is trying to move this way. So the static friction is still technically opposing the motion. And yeah, if this is a bit confusing, like I said earlier, I will talk about this more in a later video. And anyways, on to the next force. So we covered kinetic friction and static friction, and next up is spring force. And honestly, I prefer to call this the restoring force because it actually works for a lot of objects, not just springs. Any object that has like some sort of oscillatory motion or like harmonic motion, um, this force would apply. But yeah, it's known as the spring force, and some people, myself included, prefer to call it the restoring force. But it's easiest to explain using springs, so I'm just gonna use springs. Okay, so let's say I have a flat surface and I have a spring like this, and let's say this is the equilibrium position. In other words, this is sort of the default length, and it's not being stretched or compressed, so this is where it's normally at. And now let's say I stretch the string or displace it by some value delta x. Well, then the restoring force, and you can see why it's called restoring force, because it tries to get a spring back to equilibrium, would just be k delta x. And the opposite also applies. If I were to compress the spring, okay, that was terribly drawn, but oh well. If I was to compress the spring by delta x, the magnitude of the restoring force would also be k delta x, but this time the direction would be this way. So basically, the restoring force is kind of self-explanatory. That's why I prefer calling it restoring force instead of spring force. And it basically just tries to restore the object to its equilibrium position. And obviously, it's not going to instantly go to the equilibrium position. It will oscillate around it, but it will eventually reach it. And yes, as I said earlier, this doesn't just apply to spring. So it works for anything where there's some kind of oscillatory motion. So what does K mean? Well, K is just called a spring constant, and like I said earlier, it does not apply just to springs. It's just most commonly used for springs. And K depends on like what material the spring is made out of, and also how long the spring is. And it's usually given to you in problems. So yeah, that is spring force, tension, friction, gravitational force, and normal force. And I did make another video. It's I believe it's in my fluids playlist on buoyant force, so I'm not going to be talking about buoyant force, but if you want to learn more about it, you can check out that playlist. And finally, the next force is the centripetal force, not to be mistaken for the centrifugal force, which is a fictitious force. But the centripetal force, it's not really a specific force. It's more of like a general force for a certain scenario. And I'll explain what I mean by that. But basically, the formula is mv squared over r. Basically, if an object is moving in a circle or some sort of round or round path, then so basically, I said in my first video, acceleration is the change in velocity with respect to time, and velocity is both speed and direction, which means that an object doesn't necessarily have to change its speed to be accelerating. It can change its direction. And in fact, there's something called uniform circular motion. And what that is it's kind of self-explanatory, but if an object is moving in a in a perfect circle and it's at a constant speed, it would still be accelerating, and the acceleration would be pointing right in the center. And since the speed is not changing, there's no tangential acceleration or no tangential component of the acceleration. So basically, this applies. So centripetal force basically is just a force that um, is exerted on you when you're changing direction, or that you must exert to change direction, I should say. And it isn't really a specific force. For instance, if you have something attached to a spring and you're like making it go in circles, then in that case the tension would actually be centripetal force. Or if something is orbiting, planet is orbiting a sun, in that case we could say that gravity is the centripetal force. So yeah, it's not really a force. Okay, it is a force. It's not a specific type of force. It's just a force that depends on situations. So mv squared over r is just the radius, v is the velocity, or no, speed actually. V is the speed. Well, it doesn't really matter since it's being squared. So a negative squared would still be positive, but it's actually the speed. And r is just the radius, m is the mass. And notice, using the Second's law, we can also find the centripetal acceleration, which is just v squared over r, since Newton's second law, as I said earlier, is that force is mass times acceleration. And if you're not moving in a perfect circle, let's say your velocity does change and you're moving like this, then you would have a tangential component to your acceleration, but there would still be some centripetal acceleration. And your actual acceleration is actually sort of made up, comprised of these two components. So yeah, that's the radial acceleration, that's tangential. And yeah, so these are the basic forces, or the most common ones. There are some others like buoyant force, but yeah. Okay, now we will be discussing free body diagrams. And actually, I already drew some. A free body diagram is just a way to. It's basically you just draw a diagram of an object and which force are acting on it to find out like things like its acceleration and stuff like that. And I'll talk about it more once we do some practice problems. Okay, next is also Atwood's machines, which is just a fancy term for a pulley with masses. And yeah, so this is just some terminology. And basically, in addition to the forces I talked about, well, not really in addition, but there's actually four main forces in the universe. And every single one of the forces I mentioned is like falls into one of these four forces. Like these are the general forces, and every force is sort of some category of these forces. Well, first of all, is gravitational force, and I already talked about that. Next is electromagnetic force. And since this is mechanics, I didn't really discuss the electric force, but I will discuss it in eventually in my electromagnetism playlist. So yeah, and there's also magnetic force, and well, usually in school you're gonna be taught of the electric force and magnetic force as being separate forces, but they're actually one force, but they're sort of combined. And so a little bit about the electromagnetic force is that it's actually in several everyday interactions. For instance, tension. So tension is actually just electric forces holding the like atoms of a string together. So tension can be construed to be a type of electromagnetic force. Okay, next force is weak force. And I have no idea why I suddenly started writing in cursive, but yeah. The weak force is just responsible for everyday nuclear processes. Actually, no, it's not everyday, but various nuclear processes. And it doesn't show up much in problems, and it's not really something you see a lot in everyday life. And because there has to be a weak force, there's obviously also a strong force. Okay, this strong force is pretty important because it's actually what holds protons and neutrons together in the nucleus of an atom. And yeah, so basically we wouldn't have much around if we didn't have the strong force. Okay, so now we are going to be doing some practice problems. So let me just clean up everything so I have space. Alright. The first one, two people pull on opposite ends of a rope. Please forgive my terrible drawing. Each with a force F. So that's F, and that's F. The tension in the rope is blank. That is an excellent question. So the tension, okay, so the options for this are the tension is either F over 2, F, or 2F. And the answer is actually the tension is just F. And the reason for this is because when we look at the tension, we look at like the part where the force is being exerted. Sort of. So there's a tension here, which counteracts this force, and tension here. And yeah. Also, it wouldn't really make sense for the tension to be F over 2, because so if we did have F over 2, well then this part would be accelerating this way, and this part would be accelerating this way, and they would sort of cancel out, but the spring, or sorry, the rope would sort of be stretched, and yeah. Same thing with 2F. Okay, yeah, so that's the first problem. Okay, the second problem. So you have a flat surface, some mass m, and then lowercase m. And you have some force F exerted on the lower mass. You accelerate the two blocks by pushing on the bottom block with a force F. The top block moves along with the bottom block. What force directly causes the top block to accelerate? Well, that's a great question. So, as we know, force is mass times acceleration. So something has to be pushing on the top block for it to accelerate. But you're not making contact with the top block. So what could it be? Well, the answer is friction. It's kind of obvious if you think about it because, so let's say there is no friction. So then we have this block, we have this block. If there's no friction, then there's no net force acting on this top block, right? So then it would just stay in position while this block would slide. Well, not slide, but it would move, and yeah, this would just stay here and it would fall. So then some sort of friction has to be keeping it on. But now the question is, what type of friction is it? And the answer is static friction, because sure, this block is moving, but relative to the surface for this block, well, the surface for this block is this block, the big block, or the bottom block. And relative to that, the little block is not moving. So if we look at it relatively, then there'd have to be a static friction. Sorry, yeah, okay, actually, I don't know why I crossed that out, but there'd have to be a static friction pushing the little block that way, not kinetic friction. It's easy to think it's kinetic since the big block's moving, but it's actually static since relative to the big block, the little block is not moving. Okay, so yeah, those are the first two problems. Nothing terribly difficult. Okay, next problem. So we have a block with mass m, a block with mass 2m, and another one with mass 3m. And we have a force F. Okay. three boxes are pushed with force F across a frictionless table. So I'll just say mu0. Across a frictionless table, let n sub 1 be the normal force between the left two boxes. So these two are exerting normal forces of n sub 1 on each other. And let's see, let n sub 2 be a normal force between the right two boxes. So these are exerting normal force of n sub 2 on each other. Then, okay, and then so the question gives us four options. And option number 1 is that f is equal to n sub 1, which is equal to n sub 2. Option B is f plus n sub 1 is equal to n sub 2. And C, sorry, I lost my train of thought. C is f is greater than n sub 1, which is equal to n sub 2. D is f is less than n sub 1, which is less than n sub 2. And finally, E is that f is greater than n sub 1, which is greater than n sub 2. Okay. Well, actually, as soon as I saw D, I could immediately tell that it was cap. Because, so, say that f is less than n sub 1, right? But then n sub 1 would be pushed back here on this block. And if n sub 1 was greater than f, then this block would be accelerating this way, which makes no sense. Like, if you just think about it intuitively, if you were pushing on a block and it just suddenly got pushed back like that, yeah, that's cap. Okay, and then just from looking at the problem, I think E is the correct answer. And we can actually sort of break this down. So, okay, so let's say that the whole system has some acceleration A. Well then, using Newton's second law, F would just have to be 6ma, right? Because the total mass of this system is 6m, and then we said Newton's second law, F is equal to ma, assuming m is constant, which in this case it is. Okay, now let's ignore the first block and look at these two. Well, whatever force is exerted on these two would have to be equal to 5ma, since all three of these have the same acceleration, and acceleration is force over mass, and the mass of this is 5m, so the acceleration would have to be 5ma. And the force that is acting on this double block system is just n1, so we know that n1 is 5ma. And finally, okay, we're gonna do that. And let me change colors. Okay, now let's only look at this final block here with 3m. Now we know that the force on this has to equal to 3ma, since its acceleration has to be the same as that of these other blocks, which is a. And the force that's being exerted on this is n2, so we know that n2 is 3ma. And as we can see, E is indeed the correct answer. So yeah, and okay, let's see what's next. Okay, now we're actually gonna deal with actual like numbers. So it's not gonna be conceptual, or it's not gonna be as conceptual. Okay, so we have two boxes or two blocks. One is 2 kilograms, and the other is 1 kilogram. And we have a force of 3 newtons exerted on them. What is the normal force between the blocks? And we can actually do the exact same thing we did in the previous problem. And so first of all, using Newton's second law, we know that acceleration is the sum of forces over mass, and total mass is 3 kilograms, sum of forces, well, there's only one force, it's 3 newtons. The acceleration is 1 meters per second squared, which means each of these has to be traveling at 1 meters per second squared. And we know that this force is only exerted here. So let's now look at this block. It also has to have an acceleration of 1 meter squared. And the force that is being exerted on is the normal force of the first block on it. And for this to be accelerating at 1 meters per second squared, we know that F is equal to ma, and in this case, it's 1 times 1. So the force is just 1 newton. So, and then by Newton's third law, the normal force between the blocks would have to be the same regardless of which block is exerting it on the other block, because equal and opposite forces. So the force that this exerts here is also 1 newton. Which means then that the normal force between the blocks is 1 newton. Okay. For our next problem, we have mass m, another mass 2m. Sorry if I sound sort of lethargic. My throat is starting to get tired of this. Okay, and then we're just pulling on it. So mass m, mass 2m, and then there's some tension between them. And it's saying that the ground is frictionless, so it means the coefficient of, regardless of whether it's kinetic or static friction, has to be 0. And the string connecting the blocks is massless. If you accelerate the system to the right as shown, the tension is the same everywhere throughout the string, connecting the masses because A, the string is massless, B, the ground is frictionless, C, the ratio of the mass is 2 to 1, D, the acceleration of the system is non-zero, or E, the tension is the same throughout any string, no conditions are necessary. And as I said in like the first problem we did, the tension has to be same throughout the string because it's made of the same material, and it's by like the individual components of that material. So it's E. Okay, next one is a bit more conceptual. You are in a plane accelerating down a runway during takeoff, and you are holding a pendulum, say a shoe hanging from a shoelace. The string of the pendulum A hangs straight downwards. B hangs downward and forward, because the net force on the pendulum must be 0. C hangs downward and forward, because the net force must be non-zero. D hangs downwards and backwards, because the net force must be 0. Or E hangs downwards and backwards, because the net force must be non-zero. So I suck at drawing, so I'm just going to draw the plane as a long box, and let's say this box is accelerating as the problem specified. And actually, this sort of problem, I'll talk about it more when we get to fictitious forces. But for now, let's not. Okay, so, and let's say this is my hand, and I'm not going to draw myself, but this is my hand, and this is the shoe, and that's the shoelace. Okay, and let's see what the problem's asking. The string of the pendulum, okay, so it's asking how it hangs. Okay, so we know the plane is accelerating this way. And assuming that there's enough friction on the ground, I would also be accelerating this way. And I'm holding the strings, so it should be accelerating this way. But, well, intuitively, we would know if we imagine it that it hangs downwards and backwards. And the reason for this is because, okay, so this would be resisting a change in motion. Or like, okay, how do I explain it? Okay, so well, first of all, it has to be E, because the net force on the shoe is non-zero because there's some tension. But the reason it's hanging backwards is because it's resisting the rest of the motion of the plane. And this resistance to change in motion is called inertia. And it's also called mass. So mass is sort of the same thing, I guess. Okay, whatever. So next problem. When you stand at rest on a floor, you exert a downward normal force on the floor. Does this force cause the earth to accelerate in a downward direction? So yeah, I already talked about this earlier, but the way your weight is measured is actually by the normal force that you exert on the ground, or the weighing scale rather. And yeah, so the problem is asking, does this force cause the ground to accelerate? Okay, let's look at the options. So A says that yes, it does, but the Earth is very massive, so you don't notice the motion. B says yes, but you accelerate along with the Earth, so you don't notice the motion. C says no, the normal force isn't a real force. Yes, it is. So C is wrong. D says no because you're pulling on the Earth gravitationally, and E says no because just friction at your feet. Okay, that makes zero sense. So E is wrong. And I'm thinking it's D. And for this, we'd have to use Newton's third law to see why, and also sort of the second law. Okay, so first off, let's look at the forces that the Earth is exerting on you. So I'm going to sort of color code this. So blue means that it's the Earth on you, and if I'm writing it in, actually, let me use gray, you on Earth. In other words, the forces you're exerting on Earth. So let me actually just change this. Okay, so you are exerting a normal force on the Earth, but you are also exerting a gravitational force, which counteracts the normal force. Now this prompts that you stand at rest on the floor. And now if we look at the force the Earth exerts on you, it also exerts a normal force. By Newton's third law, these two have to be the same. So this is a Newton's third law pair. And the Earth also exerts a gravitational force on you. And by Newton's third law, these two have to be the same. And here's the thing, the problem said that you're at rest, so these two have to be equal in magnitude, which means that these cancel out. But because these are Newton's third law's pairs, these two also have to be equal in magnitude, so these two would have to cancel out. So the answer is D, because you are pulling on the Earth gravitationally, and that cancels out the normal force that you are exerting on the Earth. Okay, let's see what problem is next. Okay, it's another third law problem. So let me change it to yellow because I like yellow. And also it's a stimulating color. Serious, actually it's an improvement that it stimulates you. Whereas blue is actually sort of a common color. Okay, anyways, but I digress. So the problem says if you stand at rest on a bench, the bench exerts a normal force on you. Yeah, sounds fair enough. So this is the normal force the bench exerts on you. What force is related to this normal force when used third law? And so the options this question gives are A, the gravitational force from the Earth on you, B, the gravitational force from you on the Earth, C, the normal force from you on the bench, or D, none of the above. And as I said, well, Newton's third law says that every force has an equal and opposite force. And the gravitational forces are not normal forces. So the answer would be the normal force you exert on the bench. And actually, a more quantitative way to say Newton's third law is the force is exerted by F of, or the force of object 1 on object 2 is equal in magnitude to the force of object 2 on object 1. And if you wanted to put that in vectors, since it's in the opposite direction, it would be negative of the force of object 2 on object 1. So the normal force, the bench is exerting a normal force on you, and you're exerting a normal force back on the bench. And that is a Newton's third law pair. If they're not the same type of forces, then it wouldn't be considered Newton's third law. Well, there are some exceptions, but usually that's the general rule. Also, it wouldn't really make sense. Sorry, option B wouldn't make sense, and B says the gravitational force from you onto the Earth, because, well, the Earth isn't the other object in this situation. Right now, we're looking at you and the bench, and so that's how a pair works. Like, you exert a force on it, and it exerts a force back on you. Okay. The driver of a car steps on the gas, and the car accelerates with acceleration A. Okay, so such a terrible drawing. Okay, yeah, that was bad. Okay, so it's accelerating with acceleration A. When writing the horizontal F equals ma equation for the car, and it's horizontal, so I'll just put that subscript. Um, the F acting on the car is blank. So A is the normal force between the tires and the ground. Okay, so that is obviously cap because the normal force is perpendicular to the ground, which if I didn't draw it so terribly, it's supposed to be horizontal. So normal force would be pushing the car upwards. So right now we're looking at the horizontal forces. So A is cap, and if we look at B, the friction force between the tires and the ground, that is likely the correct answer. As I said earlier, static friction is what's like pushing the car forward. C, the energy between the driver's foot and the pedal. Or sorry, not energy, the force between driver's foot and the pedal. That would also be cap. Like, you are not strong enough to push a car. And to say that that acceleration is caused by the force on the pedal, no. The force of the foot on the pedal does start a chain of, like, events. I don't really know the specific details. I mean, I know that there's an axle, and I know that gases are heated up, which causes some sort of thing with pistons and something to do with the axle rotating. But yeah, I don't really know the specifics. But one thing for sure is that you cannot move a car, especially just by pushing on it on the pedal with your foot. Like, that is ridiculous. So that's C is obviously not correct. D, the energy by burning the gasoline. Well, the energy does cause the car to move, but right now it's asking what the force is. So this is one of those where you have to actually pay close attention to wording. Well, not really even close attention, but like just attention. So it's kind of common sense because yes, it's energy, it's not force. Okay, and then E, the backwards friction force that balances the forward ma force. Well, didn't the problem literally ask what force was causing the ma? So how would the backward friction force, which balances the ma force, be the ma force? So yeah, that makes no sense. So the answer is B. Okay, let's see. Okay, next one is I actually do not know the answer for sure, so I'll be sure to check the answer. But it says the static force between a car's tires and the ground can do all of the following except A, speed the car up. Well, yeah, I know for sure A has to be right. Or not right, because it's asking except, so A has to technically be wrong. B, okay, so A is speed the car up, B is slow the car down, C is change the car's direction, D is it can do all of the above things. I don't know actually. Okay, so we know for sure the answer is in A. Okay, so if this car slows down, actually no, static friction could cause the car to slow down, right? Or wait, no, wait. Okay, I think I'm tripping. Okay, so when you hit the brakes, the car's wheels don't move, which causes a kinetic friction to be moving that way, which means there is no sag friction because it's moving. And yeah, okay, so I think the answer would be B. I'm going to have to double check that one. Okay, let's see. Okay, finally an inclined plane problem. Fine. Okay, so we have an inclined plane, and actually let me read the problem. A block is at rest on a plane inclined at angle theta. The forces on it are the gravitational, normal, and friction forces. Which of the following statements is always true for any data? And let me actually draw a better ramp or inclined plane. So, okay, so it's angle of incline is theta, and we have the object. And as I said earlier, normal force is perpendicular to the surface. Gravitational force, on the other hand, is like always downwards. And since it would naturally move this way due to components of the gravitational force, oh, and by the way, this is a similar triangle. So technically, this would be mg cosine theta, and this would be mg sine theta, which is pretty neat, nice to know. And mg sine theta would actually be causing the block to move this way. So the friction would oppose the motion, which means then the problem didn't specify if it's static or kinetic. So I'm just gonna say friction, which means that the friction is this way. And it's asking which of the following statements is always true for any data. Okay, so the choices are A, and A says that the gravitational force is always less than or equal to the normal force. And I know for sure that that is not true. And also it says that the gravitational force is always less than or equal to friction. Okay, B says gravitational force is always greater than or equal to normal force, and that it's always greater than or equal to the friction. And from what I know, I'm almost certain it's B. But let's look at all the options. C says that the force of the friction is equal to the normal force, and D says that force of the friction plus the normal force is equal to the gravitational force. And finally, E says that the force of friction is greater than normal force if coefficient of sag friction is greater than 1. Okie dokie. Okay, let me just look at the problem again. Oh, yeah, and the problem says that the block is at rest, so that's important to know. So it's basically asking which one of these works for any angle of incline. And I know for certain it's B, but I'm going to explain why. Okay, so as I said earlier, this is a similar triangle if you break down the gravitational force into its components. And because it's at rest, these two forces have to cancel out. So we know that N is mg cosine theta. And notice that this force also has to cancel out with the friction for it to be at rest. Actually, no, then this would be static friction since it's at rest. So in that case, we know that the static friction has to be mg sine theta. And yeah, so all we have to do is use these equations. Oh yeah, okay, so sorry, I lost my train of thought. So the reason why mg is always greater than or equal to n, or this is always greater than or equal to this is, well, first of all, let's look at the range for sine and cosine. We know that both of these are always bounded between -1 and 1. It's just a basic trig fact. But since we're looking at the magnitudes of the forces, we can just say that it's bounded between 0 and 1. So let's consider theta being, well, let's look at the extreme. So first, let's say theta is 90 degrees. If theta is 90 degrees, then we know that the cosine of 90 is just 0, so there's no normal force. And if theta was 90 degrees, then the block would literally just be falling down, because there'd be no ramp, there'd be no inclined plane. On the other hand, the other limiting case would be if it's 0 degrees, where there would also be no ramp. And if it was 0 degrees, sine of 0 is 0, so there would be 0 static friction, since there are no other horizontal forces acting, which makes sense. And since these are both 0, but gravitational force is still being exerted on the block in both of these scenarios, we know then that A cannot be true, because in both of the limiting cases, we can see that gravitational force is greater than normal force and static friction respectively. But here, since the normal force is always greater or equal to gravitational force, or static friction is always greater or equal to friction, or sorry, greater than or equal to gravitational force. So A is obviously not true. And just from knowing how like theta works, well, we can obviously see B has to always be true. And C, so as I said earlier, the static friction is just equal to, well, it's less than or equal to this. And we said normal is mg cosine theta, so we have this. And this would have to be equal to the normal force, which is mg sine theta. And we can see that this would only work for a specific angle. Like, yeah, this would not always work. But it's asking for something universal that applies for any theta. This is wrong. This is obviously not wrong. I mean, they're not even pointing in the same direction. So, okay, in this one, this does not work for any theta. As I said earlier, it has to be a specific theta for this one to work, so this is wrong. Okay, did I run out of space? Oh, no, okay. Next problem. A block sits on a plane, and there's friction between the plane and the block. So I'll just give it an angle of incline. And we have a block, and we have some friction. There's friction between the block and the plane. The plane is accelerated to the right. If the block remains at the same position on the plane, which of the following pictures might show the free body diagram for the block? Actually, yeah, I'm not gonna draw out all the options, so I'll just. Okay, so I'm just gonna draw out each of the options with the block, but pretend that the plane's still there. I'm just gonna do this to save time, but so first option says that there's a normal force, there's also the friction force, and then there's the force of that, and finally there is mg. And actually, just from looking at all the options, the rest of them are just blatantly wrong. So yeah, it's definitely E, because if we look at the components, this would cancel out with this component, or sorry, it's not even a component, this force here, which is perfectly horizontal, it would cancel out with this component of the friction. Actually, no, this force added with the component of normal force would cancel out the friction, and then the vertical component of the normal force would cancel out with, or the vertical component of the normal force plus the vertical component of the friction cancel out with the gravitational force. So yeah, the answer is A. Okay. Next one. A block with mass m sits on a frictionless plane. Okay, I'm getting quite a bit of frictionless plane problems now. Okay, sits on a frictionless plane, inclined at angle theta, and if the plane is accelerated to the right with the proper acceleration that causes the block to remain at the same position with respect to the plane, what is the normal force between the block and the plane? Hmm. Actually, no, I think it's the normal force is always mg cosine theta because, as I said earlier, if we have the block and we have mg and there's a similar triangle, so this is also theta, and then this would have to be mg cosine theta. But then there's also the normal force, which is perpendicular to the plane, which this would have to cancel out with. And with respect to the plane, the block isn't moving, and so the normal force would not be changing. So yeah, it would have to be n is mg cosine theta. Okay, this one is interesting. So a bead is arranged to move with constant speed around a loop that lies in the vertical plane. So we have the loop, and we have some bead here that moves. I didn't specify it was clockwise or counterclockwise, but since it's speed, it does not matter because speed does not have a direction. Okay, so the magnitude of the net force on the bead is A, largest at the bottom, B, largest at the top, C, largest at side points, or D, same at all points. Well, actually, the problem says that the bead has constant speed. And for it to have constant speed, that means there's no tangential acceleration on it. Which means then that the only acceleration would have to be radial acceleration. So while the velocity is changing, it's because the direction is changing, not the speed. Which means then that the force would have to be the same throughout. So it's the same at all points, so the answer is D. Okay. Alright, next one. A toy race car travels through a loop-de-loop, which is just a circle in a vertical plane, on a track. Assume that the speed at the top of the loop is above the threshold to remain in contact with the track. The car's acceleration is blank. Okay, so we have loop de loop. Kind of reminds me of that one SpongeBob episode where like he was trying to learn how to tie shoes or something like that, and then they had a song about loops. But I digress. Okay, so the car's at the top of the loop, and there's the gravitational force. And let me reread the prompt. So it says, assuming that the speed is above the threshold to remain in contact with the track, the acceleration is blank. I think I'm pretty sure it would just be, let's see, okay, so it's at the top of the loop, and, well, right at the instant it leaves the top, there would also be a normal force, which is less than the gravitational force, and so we know that the acceleration is sum of forces over mass, which would be mg minus m, sorry, mg minus n over m, which is g minus m over m. So this would be the acceleration. So it's downwards and smaller than G. The answer is B. Okay. Wow, that's a lot of problems. Interesting. This one looks. Okay, actually, let's just. I'm gonna skip some problems because I'm basically repeating the same concept over and over again. So let's try some spring problems. So a mass hangs from a spring and oscillates vertically. The top end of the spring is attached to the top of a box, and the box is placed on a scale as shown in figure 4.8, which I'll just draw here. The reading on the scale is largest when the mass is A at its maximum height, B at its minimum height, C at the midpoint of its motion, or D all points at the same reading. So let's draw our scale, which measures, does it measure mass or weight? It didn't specify, but I'm gonna assume it measures the weight. Actually, no, I said it measures the normal force exerted, so yeah, that's what I'm gonna assume is the case here. Okay, so we have our spring, and we have the mass at the end of the spring, and it oscillates up and down. Okay, let's call this the equilibrium position, or in other words, the quote-unquote default position. So when the mass is here, sorry. So when the mass is here, the restoring force that is exerted on it, well, let's call this delta y. Well, then the restoring force that pushes the mass up would just be k delta y. And if it's up here, and it's delta y again above the equilibrium position, it would be pushed down k delta y. I think it should not matter actually, since only the box is in contact. Yeah, I don't know. This is a bit of a tricky conceptual one. Um, hmm. Okay, so if it's stretched all the way and there's a force k delta y, well, the spring is attached to the box here, and the box is what's keeping the spring from just detaching. So then, the box would be exerting that force of k delta y to keep the spring from detaching. Which means then that a force of k delta y would be exerted back on the box right when the spring is at its lowest position. And using the same logic, a force of k delta y would have to be exerted upwards on the box when the spring is at its highest position, I think. Um, okay, so the normal force when it's at, so we're gonna split up. So when the spring is at its default position, the normal force on the scale would just be mg. When the spring is at its lowest position, it would be mg plus k delta y. And when it's at its highest position, it would be mg minus k delta y. And the problem is asking us when the reading is the largest. So it would have to be, sorry, it would have to be at the lowest position. So B, actually let me just leave a star so I know that I have to double check this one. Okay, what else? Okay, let's do another spring one. So a spring with spring constant K hangs vertically from the ceiling, initially at its relaxed length. You attach a mass m to the end and bring down it to a position that is 3 mg over K below the initial position. So let me just draw that out. Okay. And let's say this is the equilibrium position, and it's moved down by 3 mg over K. Great, okay. And you then let go. What is the upwards acceleration of the mass right as you let go? Oh, okay, this one's actually pretty easy. So at the moment, let's look at the mass and draw a free body diagram. Well, there's mg, and there's also the restoring force, or the spring force, which we said is k times the displacement, which is just 3 mg over k. And so we can see this actually cancels out neatly. So the net vertical force then would just be 3 mg minus mg, which is 2 mg. And we know that acceleration by Newton's second law is just force over mass, 2 mg over m. So it accelerates upwards by g. And yeah, so the answer is B for that one. Okay, now let's do some pulley problems. I'll do a relatively easy one because pulleys can get super annoying. Okay, so we have a pulley here which is attached to another pulley like this. Then we have some mass over here, and then just a string from this pulley which is connected to another pulley here which has two masses. And this one accelerates upwards with acceleration a1. This one accelerates with acceleration a2. And this one accelerates with acceleration a3. Okay, and then it's asking, what is the conservation of string relation? Okay, so basically conservation of string is, oh shoot, okay, I just realized there's also another string here. That would have been weird if this one was just floating in the air. Anyway, so conservation of string is just the idea that it's just pretty self-explanatory. You have to save the amount of string, or you have to account for string in your calculations and assume that it can't be stretched or compressed. So and it's actually pretty useful for seeing how the accelerations are related. So first, let us, instead of thinking of it in terms of accelerations, let's think of it in terms of displacement. So let's say that this mass moves upwards by some displacement x sub 1. And this mass, by that I mean this mass and that mass. So the left mass moves up by some distance x sub 2. Well, technically it's y sub 1, y sub 2 since it's vertical, but oh well. Well, to keep the string from being compressed, okay, how do I do this actually? Okay, yeah, so to keep the string from being compressed, the entire pulley would actually have to move up by the average of those two, x sub 1 plus x sub 2 over 2. And we can see this if you think about it intuitively, you can see this, but even if we use actual numbers, we can see it. So let's say the total length of the string is 10. And I don't really care about units, but because this is like hypothetical, but And now let's say this part moves up by 3 and this part moves up by 4. So, well, then we can say that it would not be conserved because the spring would suddenly be compressed so it goes down to 3. But what if we move the pulley up by 7 to save string? Well, that would not. Wait, actually. Um, okay, so if we moved it up by 7, the problem is that these would each get 7 units longer, which means we would actually have 3 plus 14, which is 17, which is actually now we're having extra string. So we'd actually have to move it by the average of these two. So for instance, if we moved it up by 3.5, well now each one would get 3.5 units longer. So we'd have 3 plus 2 times 3.5, which gets us back to our original length of 10. Okay, so with that being said, this pulley would have to move up by x sub 1 plus x sub 2 over 2. And we can actually take the time derivative of this. And if we do that, so we have the double time derivative of x sub 1 plus the double time derivative of x sub 2 over 2. And that's the acceleration of, well, actually, let's call this pulley 1, pulley 2, pulley 3. So we're going to see that's the acceleration of pulley 3. Okay, and dang it, I suck at pulley problems. Okay, let's see, how do we do this? So we know this is moving upwards, and we want to save string, which means that this would, okay, so this pulley would also have to be moving upwards at the same acceleration to save string. So then we have that this is also equal to the acceleration of pulley 1. But then the only thing that's feeding string for this to be moving upwards is this acceleration right here. And but this would be moving at its acceleration by using both sides. Because, well, that's just how pulleys work. Which means then that a sub 3 is equal to, well, the directions are opposite. Yeah, so it's negative of 1/2 of this, and well, this is acceleration, and that's acceleration. Okay, yeah, so actually no, I don't know why I put 1/2. That's not there. So an a sub 3, I think, should be negative a sub 1 plus a sub 2 over 2. And yeah, so I suck at pulleys, as you can see, but yeah, it's a little tricky to get the hang of conservation of string. And yeah, so that's pretty much it for forces. And I'll touch on like other types of forces and fictitious forces in later videos, but these are the basics. And I hoped this video was helpful, and thank you for watching.